shows the torus amplitude on solvable area in the dimension of two-dimensional conformal QC.
Is this okay? Okay, so let me first explain where this lecture fits in the school. So this week we had 4 lectures by Sasha Zamolodchikov on TT bar. And next week there are going to be 2 more by Amit Givon and then Ofer Aroni that will talk about other aspects of this, in particular string theory. And the main goal of this lecture is basically kind of as a transitional thing to develop the things that you heard from Sasha to prepare the ground for the next week. And in particular, my really main goal is to decrease by about 10% what Amit will have to say in his lecture. So that's basically where this is. Now, I want to do 3 things in this hour and a half. The first thing that I'm going to do is show that the spectrum that Sasha told us about follows from some general principles that I will explain. The second thing is, so those general principles will have to do with this torus partition sum of these models. The second thing I want to do is to study a little bit this partition sum and explain some of its properties. So that obviously, especially because of all of the confusions that we heard about earlier in the week, this is a useful thing to do, to look at concrete equations that realize all this stuff we heard about. And the last thing that is going to be very useful for Amit, I believe, is the generalization of this whole story to the case where instead of TT bar, we deform the theory by saying JT bar, where J is some current. Okay, so there's going to be 2 parts to it, the TT bar part and the JT bar part. And so let me start the first part, which I'll try to do in sort of more pedagogical detail. There are papers on all of this that I listed in the material, so you can look at more details there. But I'll try to explain this in a little bit of detail, and then the other case I will do more briefly, but you should get the idea from the first part. All right, so the starting point of the story is going to be some CFT. And I should say that everything I'm going to say is generalizable to the case where I replace this CFT to an arbitrary QFT, by which, of course, I mean, sort of by definition, a UV fixed point and an IR fixed point connected by an RG flow. So I'm not going to do this here, but it can be done, and I guess I'm contemplating whether to publish it or not. That's not in these papers, but once you understand what I'm going to do here, you're good. Now, this CFT, I'm going to assume that I can place it on a torus. So in the complex plane, excuse me, the torus is, of course, obtained by identifying the complex coordinate in this way, where tau is tau 1 plus I tau 2 is the so-called modulus of the torus. So the picture in the complex plane is like this. This is the torus, this is tau, this is the z-plane. And now I should say, to start with, this is sort of an assumption because, you know, as many of you probably know, nobody can stop me from studying theories that don't have this property. Say, the Ising model in 2 dimensions. This is all, of course, in 2 dimensions, like, you know, all this other stuff. The Ising model in 2 dimensions is described by some real fermion. And I can take, there are 3 Virasoro primaries in this theory. 1, epsilon, which is psi bar psi, and sigma, or S, whatever the spin field. And nobody can stop me from taking just these 2 and their Virasoro descendants, studying correlation functions on the plane, and nothing will go wrong. But if I want to put this theory on the torus, if I do not include this guy and all of its descendants, I'm going to run into trouble. So the assumption I'm making is that I'm not going to do such things. I'm taking the CFT to be something. And that, by the way, the trouble I'm running into if I omit this guy is that the correlation functions, partition sums, etc., that I will compute will depend on the parameterization of the torus and not be the same for torus parameterized in different ways. So I'm going to assume that I'm not going to do this. This is what this assumption means.
I guess you're also ruling out things like the free boson, where the force partition function is divergent. Like if
Well, okay, that's, well, I wouldn't put it in those words. I would say that there's a, well, you know, in string theory, we put scalar fields that are non-compact on tori all the time, and there's a story. This is not an issue here. If you want to be like mathematical, you might want to require a discrete spectrum of scaling dimensions in addition to this. I don't want to go there. Well, I mean, let's require it. This is not going to be a big issue in this particular conversation. So yeah, so we're going to assume this. And what this means, like I said, the hero of the story is going to be the torus partition sum. And so if we do this, this is more or less the same thing as requiring that the partition sum, which I will denote by Z0 because, well, it will be clear soon why I put the 0 here, is modular invariant. And when I write Z of tau here, I don't mean that it's holomorphic. It's a function of tau and tau bar. And AD minus BC is 1 with these things being integer. So that's the usual story of modular invariance, of partition sums in conformal field theory. Remember, it's going to be useful to remember what this Z0 is. This partition sum in some Hamiltonian formulation can be thought of as the sum over all the states of, just get the factors straight, e to the 2 pi I tau 1 r times Pn minus 2 pi tau 2 r times En. So Pn and En are the energies of states. Of course, this tau is tau 1 plus I tau 2, like I said. And in a conformal field theory, all these things, the r times Pn and r times En, are independent of the radius. That's what conformal invariance means. And they're related to the L0 and L0 bar eigenvalues. So L0 minus L0 bar is, I guess, r times Pn, and L0 plus L0 bar minus C over 12 is r times En. So this is kind of the starting point of this whole story. So any questions about conformal field theory? Okay, so now the question that we want to ask is the following. So the question we want to ask is what happens when we deform this structure? What happens when we deform the structure in the way that, kind of the rough way that Sasha was talking about? So we want to add to the Lagrangian a term that I will write like this. So there's some operator whose dimension is delta comma delta. I will assume that delta is larger than 1, so it's irrelevant. So the coupling has dimension 1 minus delta, 1 minus delta. And there are corrections, as we heard, that go like higher powers of this t. So this is something that, as we heard in detail, is not advisable in general. But what we are going to do is ask, can we do this and get away with it in the following sense? So we're going to require 3 things from the resulting structure. So I'll first list these requirements and then talk about them a little bit. So the first requirement is that the deformed theory, and by the way, I'm not assuming anything about this delta at this point other than this here. So the first requirement is that the deformed theory is a well-defined theory with one scale associated with this coupling. At least to all orders in perturbation theory in this T. So I'll talk about it a little bit. The second requirement is that much like the original theory we started with, it is modular invariant with the coupling transforming appropriately. I'll talk about that in a second. And the third requirement is that the energies of states in the deformed theory are only functions. So I'll explain precisely what I mean by this, of the undeformed spectrum. So what we're going to do is show that these 3 conditions determine uniquely everything that this torus is about. So the precise formula for the partition sum and therefore the precise spectrum of the theory. But before I show this, let me say a few words about what these assumptions mean and why we expect them to be valid here. So let's talk about them in turn. So the first assumption, so, well, on some level, Sasha talked about this a lot. So, you know, if you do this, in general, you will have to introduce an infinite number of couplings. You will get a theory with an infinite number of scales that furthermore depends on the UV cutoff. So this basically is just the statement that the deformed theory exists at all, as he said. If this is not true, this assumption 1, then we're just talking about the generic irrelevant deformation. So you have to specify a UV cutoff and the usual story that we, the whole point is that we don't need to do here. Now, I want to stress, as he did as well, this is a strong assumption, but it's a qualitative assumption. So it's surprising that making some qualitative assumptions will give you some, you know, exact quantitative results. So it's actually going to happen here. So the second assumption here is the following. So this is this modular invariance business. Now, so what I'm going to do for simplicity is set delta to be 2. Here, remember I said before that I don't need to make any assumptions on this delta or the operator O, other of course than this fact that the theory exists. I'm going to set it to 2 because that's the case for TT bar, but everything I'm going to say is, I'll be with you in a second. Everything I'm going to say doesn't depend on this assumption. I'm trying to save some time and chalk here. Yeah. That's a what? Yeah, this is, when I say dimension, I mean energy dimension. In 2 dimensions, of course, there's a left and right moving dimension.
I mean, for O, it's a scaling dimension. That was a scaling dimension.
Yes. So as opposed to what?
No, I mean, for T, it's not, the T doesn't scale, right? It's the mass dimension.
T? Oh, little t. Well, okay, yeah. No, what I meant is, in the same sense as if you write some massive Klein-Gordon field, then the mass has units of energy. So correlation functions depend on, say, the separations times the mass, this kind of thing.
David, when you say that this is applicable for any delta, do you mean that one doesn't care about the properties of 2? That the assumption 1 will be you will be able to have assumption 1 work out doesn't depend on the properties of what you put in 2?
Okay, you're too smart for me.
We're discussing arithmetic properties of 2.
Well, okay, so let me say a sentence that I think is correct, and it may or may not be related to your question. Assuming that you found an operator O of any dimension larger than 1, for which you can do this deformation and you get something that satisfies this assumption, we will discover in the end that delta has to be 2 and the operator O has to be TT bar. In other words, the statement that delta is equal to 2 is going to be not an input but an output. Is that, does that help? Or
No, it helps because before it seemed to me you're saying that you don't care what delta is.
So for the analysis, the value of delta is not going to be assumed, but the output of the analysis is that the only case that works is delta equals to 2. And
So what about 1.5 for JC?
yeah, so I should say in this particular case, we are assuming Lorentz invariance. And the statement I just made is assuming that if Lorentz invariance is not valid, we will have to have a separate conversation. And that's one thing. But the other thing is that, I think there's one more thing, but it's not a good time to mention it because the players haven't appeared yet on the field, so they can't score goals.
But if O were relevant, then you would say that it's kind of obvious that 1 through 3 is true?
No. Let me perhaps, I'll address this when I talk about the place where the statement fails. So, so like I said, I'm setting delta equal to 2, but it's not important that I'm doing that. Again, I'm mainly saving chalk here. Say again?
I said, just want to ask a favor. There's a bad glare on the board.
On this, so you want this board to be here?
All the boards is a bit of a glare, so just kind of.
Oh, we have to switch off the light or something?
Or just say what you're...
Yeah,
It looks much better on the screen. Yeah, I'm serious.
Wait, can we switch off the light?
What
Maybe?
happens if we switch off the lights? It might
Like this light also will make for a more intimate atmosphere.
That's hard. It's too dark. It's too dark. All right, we just have to tolerate it.
So is there any side that's better than another?
That maybe is better. Yeah,
Was that the other thing you were talking about? Okay. All right. So yeah. So again, I don't want to. I basically I said this because it will appear in a moment, but you can ignore this. That's all I really wanted to say. This assumption can be ignored. Now, so I'll set this delta to 2. Now the question is, first of all, why do I expect any kind of modular properties out of this thing? So I'll say it in words because of the time I just spent on all this. The idea basically is, suppose you were to expand this in a power series in T. So at every order in T, you would get some correlation functions on the torus integrated over the torus. Now, correlation functions on the torus have modular covariance properties, of course, which is something like, say, dz to the power delta, dz bar to the power delta, times the expectation value of an operator of dimension delta delta is modular invariant if z goes to z over c tau plus d, which is the standard transformation property of z. The most naive analysis you can do is just expand in whatever this O and the other things here are and integrate and just do a scaling analysis, which will give some answer that I will write in a second. So if you do that, if you now use this property and integrate, what you will find is that the partition sum of the perturbed theory satisfies the property that, like this, I'll tell you in a second what this lambda is, satisfies this property, where lambda, in terms of this t, is t divided by r squared. So the fact that delta was taken to 2 went into the fact that the number 2, so that this 2 is the same as this 2, and both of them don't matter, like I said. What else? And this r is just the size of the torus. So when I said before that the torus is
You have one equality too many.
z of this is equal to this, where lambda is the, and this lambda, by the way, has a nice physical interpretation. It's the value of the coupling at the scale r. So you can think about it. Like if it's small, then, then the coupling at the sort of kk scale is small. If it's large, the other way around, etc. So as I said, this is a kind of naive analysis. So, it involves integrating correlation functions on the torus, and integrals have been known to diverge. And so you can ask, is this naive scaling analysis valid? And I would argue that the answer is no in general, but it's the same issue as the issue, say, on the plane. So the statement that this condition 1 is valid is basically the statement that in some scheme, the naive scaling analysis is valid. Okay, so we're going to assume this because of that and proceed. I should say, by the way, that the way to think about this, we generalize the Hamiltonian interpretation from before, is that this z is the sum over all states of now some perturbed energies that, of course, will depend on lambda, on the coupling. So these guys are just some integers. They don't depend on anything. And the energy spectrum gets deformed. And we're assuming that this deformed spectrum gives rise to this kind of transformation properties. Now, you might think that if I'm going to get any kind of mileage out of this whole story, this is where I put in the answer by hand, because this is a quantitative, strong condition. But the truth is, in fact, the exact opposite of this. This is almost an empty statement, and it's the qualitative conditions, 1 and 3, where, especially 3, which we'll talk about in a moment, where most of the stuff enters. So this is actually a very weak condition on the partition sum. And for example, it's satisfied. So like you were asking before, this is actually satisfied by almost anything you can think of relevant. Say, I don't know, two-dimensional QCD will satisfy this with lambda defined appropriately. So that's not much of a constraint. Any questions about this? So let's get to this assumption 3, where most of the meat is. First of all, what is the statement? So we started with some states with energies En. They figured in the original CFT. And as I said here, the energies get deformed. And we assume that the deformed energies are given by some universal function of the undeformed energies. So if you ask where do we put in something that's most of the time is wrong, this is where. So for example, I don't know what your favorite two-dimensional Q of t is, but if you ask yourself in that theory whether this is true, it's not, okay? 99% of the time. So n labels the states. So you take some state, you know, for example, I don't know, you have a scalar field, massless, and so you look at the state alpha minus 1 acting on the vacuum. So that's a state. It has some energy, which we discussed before. And now you ask what happens to the state when we deform, when we turn on this lambda. Well, it goes to something else. And the claim is that the something else is some universal function of just the energy of this undeformed state, its momentum, and the coupling.
So the thing that it could have
the thing it could have depended on is everything else.
the OPE coefficients is the other thing. Apparently there's some function, right? So what's the thing it doesn't depend on?
All right, so
OPE coefficients, right?
you can say it this. Well, okay. OPE of what? With what?
All the operators.
Yeah, well, yeah. I mean, that's a way to say it, but I mean, it's just a complicated way of saying that this is almost never true.
Yeah.
That's you know, like I don't know. Again, just whatever field theory you like, think about, and it's not true there. So why are we assuming such a thing? Well, in the TT bar story, without even calculating a lot of matrix elements, it's clear that this is true, because you know, the things that Sasha explained in his lectures, the deformation involves bringing down TT bar at some point lambda in my notation. I should say that in lambda in my notation, and TT bar, all it knows about is the energies and the momenta of the states in the theory before you perturb it infinitesimally. So there it's true, and the only what he did when he derived the Berger's equation is basically exhibit this function. But I'm saying let's be more qualitative. Let's just assume that there's some function like this. And again, I stress this is an extremely strong assumption, which is just not true most of the time.
In particular, if n is the same n on both sides.
Yeah. Look. The n labels the states. So like in Zamolodchikov's story from earlier in the week, each state you could follow as a function of the coupling, and he exhibited for you the formula. I'll write it down a little later. So n is the same.
It's crucial that you assume that it happens. I mean, you can deform every state without limit states.
Okay, we will discuss. We will discuss this in a second. This will come up. What did I want to say? So on some level, if you wish, the question that I'm going to ask is, twofold. One, are there any other theories out there that have this property? The answer will be no. And two, can I derive everything about the spectrum and the partition sum of the TT bar model just from these assumptions? So yeah, I'll stop in a second. So again, I want to stress assumptions 1 and 3 are very strong but qualitative. Assumption 2 that looks very strong is in fact very weak but quantitative. And the meat is in 1 and 3. 2 is almost noise. Yes?
Yeah, I'm sorry. I mean, you say the answer is no, and I was going to bring this point up anyway. The answer is yes.
Okay.
Because you could think of it as an endpoint of honest randomization.
Yeah, but in those situations, well, okay, let's talk about this after I'm done, and then you can tell me, well, there's a derivation, you know. Then we can discuss what happens in those examples that you're talking about. And I think the short answer is that there are RG flows that look like they're ending, you're arriving from the TT bar direction at the infrared fixed point, but it's not, this is not true if you want to all orders in lambda. But let's talk about, look, there's not going to be any mystery.
Resilience of flows which arrive along
That's right, but why don't we, you know, this is one of those things where, you know, like speculating about what the LHC will find a year before it gets turned on. You can just wait. All right, so yeah, so that's the situation. Now, okay, so I'm going to assume those three things, and here is what I'm going to do with them. So the first thing I'm going to do is, so again, my purpose from now on is to prove the following statement, that Z of tau, well, okay, let me maybe write it here. So claim Z of tau and lambda is uniquely determined by these conditions that I stated to all orders in lambda, okay? Now, I should say the implicit here is the statement that we're going to do perturbation theory in lambda. And from my perspective, this is not some kind of technicality. The theory with finite lambda is a non-local theory, as we heard, and we're going to see here again. And it's not clear, a lot of the manipulations that one does with these theories, it's not clear why they're justified at finite lambda. So from my perspective, the sort of conservative thing to do is you study this theory in perturbation theory in lambda, and then you can try to define it for finite lambda by extending things to that case. So this is actually not some kind of technicality, but in any case, whether you think that or not, I mean, this is again just some well-defined statement. All right, so let's see how we prove this. So the basic idea is very simple. So the basic idea is, because we're doing perturbation theory, we will take these epsilon n's and expand them. So I said that they're some function of the coupling lambda. And we're going to expand this function in a power series in lambda. So we'll write things like this. En superscript k, lambda to the power k. So, you know, we have the original, these are the things that I called the En before, the energies in the CFT. Then there is the first order correction, etc. Now, if you substitute this formula into here, this will give rise to some expansion of the partition sum. which of course is driven by this expansion. So there's some expansion like this. So we have a Z0, which is the partition sum of the original CFT, which is why I called it Z0 before lambda Z1, lambda squared Z2, etc. Okay? Now, the fact that we have this modular property over here, so see lambda transforms as a modular form of weight minus 1 minus 1. So this is a form of weight minus p. And so the ZPs are weight PP forms, right? So they satisfy some condition like this. And what we're going to see is that these ZPs are uniquely determined by the conditions that I wrote down. So to get a feeling for what's happening here, I guess it's useful to write the first few terms. At least I found it useful. So let me quickly do that, and then we will see the pattern. So, you know, like if you want Z1, right, so I guess I erased the formula, but you only need to expand the energies to first order and then bring down from the exponential. So Z1 is equal to the sum over all states of minus 2 pi r tau 2 En1 times this exponential factor where these are the CFT energies. Z2, I'll just write it and stop because I want to point out some properties of those things. So I have tau 2 squared over 2 pi r, whatever, En1 squared, right? This term comes from expanding the order lambda term to second order, which is why there are 2 tau 2s here. And then there is a minus 2 pi r tau 2 En2 times the exponential, etc. So if you think about how this thing is arranged, you notice the following. So if you look at some general ZP, right? So first of all, it includes in it terms that go like tau 2 to the p, tau 2 to the p minus 1, all the way up to tau 2 to the power 1, acting on Z0. And the coefficients of each of those things are just some combinations of these energy shifts. And so they are, by this assumption, some functions of the undeformed energies, right? Now, so say the coefficient of tau 2 to the p is some operator, I claim, that I will call O1p. And this operator only depends on the derivatives with respect to tau and tau bar, right? Because when I differentiate with respect to tau and tau bar, I just bring down from the exponential p's and e's, and that's all that appears in these functions. So basically, in front of every one of those things, there is something like this. Okay, so the highest guy is this. But the basic point is that we have a power series in tau 2 times differential operators in d by d tau and d by d tau bar. And really all I used here is just the statement that everywhere I see 2 pi r En in any of these functions, I can replace it by minus d by d tau 2. And everywhere I see 2 pi I r Pn, I can replace it by d tau 1. So that's all that has happened here.
So in definite procedure, CP is even the
No. So ZP is defined in this way. So I have some partition sum that trace over the deformed energies, and I can expand this partition sum in the power series in lambda. And ZP, by definition, is a function of tau, which is the coefficient of lambda to the power p. It satisfies this property, as I explained here. It's some modular form.
What about the numerator, a tau plus b?
No. So this is just a statement that this function of tau under modular transformations transforms in this way.
Well, how does it know what's in the numerator and what's in the denominator? Like, I can, it's a fraction.
You ask how does SL to Z act?
Divide everything by a, that's the same divide the numerator and denominator by a, that's the same transformation, but you get a different.
Does that solve your problem? All right, so so that's an important point for me. So if anybody does not understand why, when I do this, expand the energies, expand the Z, then these objects, ZP, have this kind of structure. So you should ask now if you don't understand it. Say again? Yeah. So what's written here, so tau 2 times this operator they called O hat with the 1 and the P. And so basically the upper index is just telling us about the P, and the lower index goes from 1 to 2 to P. It tells us which is the coefficient of tau 2 that it multiplies, basically. So this, what's written here is O hat superscript P lower P of d by d tau and d by d tau bar. Apologize for my handwriting. Well, right now, you ask how do I know this? Yeah. Well, I basically just was being maximally stupid in my normal mode. I took these epsilon n's, I expanded them in lambda, and plugged this in. Then in the exponential, I had some expansion in the power series in lambda, and expanded the exponential. So for example, if you look at the term of order lambda to the p, you can take the term from the expansion of the epsilon that goes like lambda and expand it to pth order, etc. Okay? All right, so the claim is that if there is a solution to all the constraints are listed, in other words, if for any modular invariant Z0 there exists some differential operators O hat like this, for which ZP has this modular property, the first claim is that so if a solution exists to all these constraints that I just listed, it is unique.
Sorry, so strictly speaking, assuming that each term in that sum transforms like this is a stronger assumption than assuming that the whole sum is modular invariant.
Why do you say that?
Well, couldn't it be that somehow the different terms combine to make it modular invariant? I guess I don't see.
Well, lambda is an arbitrary real parameter.
Yeah, I guess.
I think the argument is order by order in lambda, right?
Yeah, okay. So
Yeah.
Am I understanding?
Yeah. Well, it's just that lambda is an arbitrary parameter, so
Yeah.
you cannot have cancellations that rely between different powers.
Yeah.
So I said, by the way, so these things that you were mentioning before, I think something will have to go wrong at some finite order in lambda.
Of course.
Yeah.
Immediate.
Yeah. Well, but that's, which is what I said before, that just the fact that something is arriving from the TT bar direction does not mean it's TT bar. Right?
Well, yeah.
I mean, all right. So, here we're assuming that it's TT bar. Well, I made the assumptions very precise. So Okay, so yeah, so if a solution exists, it is unique. Now, I was going to explain it more, but let me, because I don't want to keep you too long.
This is actually the most suspicious statement, right?
I mean, say it again?
That the solution is unique.
This is the most suspicious statement.
Statement, yeah.
But he's going to prove that, right?
Yeah.
Right.
Yeah.
So
Oh.
be careful, please.
Okay. Okay, so Amit, you're on your own next week.
All right.
All right, so let's do it. So I'm planning to use induction to do this. So let's do the first step of the induction. Okay. So let's look at p equals to 1. So for p equal to 1, the claim is that, just as an exercise, we didn't really need to do this, but let's do it anyway, just to get some feeling. So z1 of tau is, from here, tau2 times some operator that I called in this notation like this, acting on z0. So this is a modular invariant. It's a form weight 0, 0. This is -1, -1. This is 1, 1 from here. And so the question we're asking is, can we find a differential operator in d by d tau and d tau bar such that this whole thing is a form of weight 2, 2? Now, it's very easy to prove that the answer is that there exists a unique such operator. I'm happy to talk about it some more, but then Amit will hate me even more. And that operator, up to some overall coefficient, is just d by d tau bar. Alpha is an arbitrary coefficient, and we can set it to 1, which we will do. That's basically just a choice of normalization of this lambda. And this, yeah, I guess including the sign. So we'll do that. So this shouldn't be very controversial. Now, okay, so let's talk about the general step in the induction. The general step in the induction is, so we assume that z1 up to zp have been determined by all these constraints. And we want to show that zp plus 1 then can be as well. Okay, so how do we show this? So the basic idea of this, so unfortunately I have to erase this, although it's useful, but the basic idea is that is the following. So notice that when you look at Zp with a certain p, what enters into it is the energy shift. So Zp is sensitive to, in this notation, the energy shifts, the first order up to the pth order. So the statement that all these z's up to zp have been fixed is the same as the statement that we know all the energy shifts at order 1 up to p. And fixing this zp plus 1 is the same as fixing the next one. So zp plus 1 is also sensitive to the next guy. And so the statement that we can fix it is the statement that, given all the constraints I listed, we can fix that guy. Now, so the basic fact is that if you look at these kinds of expansions, the only place in which en p plus 1 appears in zp plus 1 is in the coefficient of tau 2. Because obviously, if we want the power lambda p plus 1, lambda to the power p plus 1, we have to take this last term that comes with the lambda to the p plus 1 and expand it to first power. So, So when we write ZP plus 1 in this way, so there's a term of order tau 2 to the p plus 1 times O hat 1 plus tau 2 to the p O hat 2, etc., up to tau 2 O hat whatever p plus 1 acting on Z0. Only this guy is sensitive to the one unknown, the new order in the energy shifts. All these guys are fixed because of the fact that we know the lower orders. So suppose we have two solutions to these constraints. Two different.
I'm sorry. You're carefully following the phase of the index p.
Oh, you want me to put the superscript as well?
Wait. I'm trying to, maybe at the expense of spending a few more seconds. What is the fate of n, the index? I mean,
No. So you see,
I want to follow how important it is that these manipulations can be done for all n.
Yeah. So n is summed over in the partition sum at each order.
How is it important that you must be able to extend the sum to infinity?
Infinity, you meaning to arbitrarily?
Summing over n.
Yeah, over all the states.
Right.
So you ask, did I, in going from here to here, make any assumptions about that?
The UV property is going to hit, right?
Well, okay. So I'm trying to do, I don't know, what in Russia would be middle school algebra, and in America it's college algebra. So I'm just, everything is on the board except for the fact that I erased it. So you're complaining that the sum might diverge?
Well, I mean...
The sum over n?
Well, I mean, it's how important it is.
Yes.
That you have to extend the sum to infinity in your
it's important to the extent that the sum is...
Instead of that, I
Yeah, cut it off.
All right, I will cut my series on
On-
first term.
Well, the place where you would be stopped before all of this, the partition sum Z0 at which you would do this would no longer be modular invariant.
Yes.
So,
Yes. Well, yes.
so that's, I'm assuming that we're not doing
All right,
such
we will
silly
come back to
things.
that. Very good.
We really don't want to talk about...
So it's important that you extend it to infinity.
The sum runs
that was my
over...
question and you answered.
Yes,
Thank you.
over all the conformal blocks, all the descendants, everything. Okay? Yeah. But yeah, again, other than that, it's just simple algebra, which of course is hard to follow on the board, but I'm not... All right, so, so like I said, we're now in the general step of this induction. And the idea is that if we have any solutions to this exercise, in other words, we found some differential operators like this, for which ZP plus 1 has the properties under the modular group I mentioned, then they can only differ, any two such solutions. So we have some ZP plus 1 and ZP plus 1 prime. So delta ZP plus 1, which is the difference between them, basically has the property that all the first terms are the same, and the only term that's different is the last one. Okay? So if there exist solutions to these constraints I mentioned, and there are two of them, then the difference between them has to have this property that it looks like tau 2 times some differential operator in d tau bar acting on Z0, and because each of them is a modular form, it's also a modular form. So this is a p plus 2 modular form. Okay? Now, such animals do not exist. It's very easy to show. I don't want to spend more time on this, but it's very easy to to show that you cannot act on a modular invariant function with just derivatives with respect to tau and tau bar. I guess the only place where they do exist, which is why I did this separately here, is this place, which is p equals 0, I guess, in that language. But for p larger than 0, there just aren't such things. So such operators do not exist. And therefore, if there is a solution to this, it is unique. Okay? Of course, I did not establish that there is a solution. It could be that there is no solution to the constraints, but there cannot be two different ones. Okay? Any questions?
Alpha is also dimensional.
No, alpha is just a number.
Yeah, but I don't understand.
Oh, sorry, this is not Sasha's alpha. I apologize.
Yes, okay, but
Mm.
O1 should have dimensionality to 2.
No. Sorry. It's not dimensionality. It's so O1 acting on Z0 is a modular form of weight 2, 2.
Okay.
Now, if Z0 is modular invariant, d by d tau bar Z0 is indeed the modular form of weight 2, 2. And alpha is just a number, which I absorbed in the definition of the coupling. Okay? Okay, so far I showed if there is a solution, it is unique. The easiest way to show that a solution exists is just to write it down. So the unique solution to all these constraints is the following. So let me first write it and then talk about it a little bit. So I claim that if you write the recursion relation I'll explain what I mean by these objects in a second. Okay, so this, so let me first write what I mean by this d tau. So these are things that work with modular forms, are familiar with them. So this is a differential operator So basically, d tau has the property that if it acts on a form of holomorphic weight k, it increases it by 2 units. And d tau bar of, let's say, k bar has the property that if it acts on an anti-holomorphic form of weight k bar, it increases it by 2 units. That's easy to show that they have this property. And so that's what I mean by this. But by the way, these factors of tau 2 are the reason why an easy way to show that this doesn't exist is to realize that what does exist is things like that, but they involve tau 2, not just derivative. Yeah, so that's what I mean by this. And so the claim to fame of this equation is the following, is if Zp is a form of weight pp, you're increasing it by 2, 2, both here and here, multiplying by tau 2, which gets it down. And so at the very least, you get a form of weight, of the right weight, of weight p plus 1, p plus 1. And it takes a little bit more work to show that it satisfies all the other constraints. Like, for example, it can be written like this, okay, with some differential operators here. Perfect. Okay, so this is a solution to all the constraints. And because of what I said before, it is unique. So we're done, in principle. So the claim is that what we've shown so far is that this partition sum that I called z of tau and lambda exists, with all the properties that I mentioned, and is unique. Now, to make the connection to what Sasha was talking about, one convenient thing is to do the following: is you write the definition of these ZPs, which are the coefficients in this expansion, like I mentioned before, and you ask, what does this recursion relation mean for the full partition sum? So, of course, it will give rise to some differential equation. Which this differential equation is d lambda of z equals to tau 2 d tau bar plus a half I d tau minus d tau bar minus 1 over tau 2. I think it's like this, parentheses, lambda d by d lambda acting on z. So the partition sum of this model satisfies this kind of differential equation, which I think if Sasha had more time, he probably would have derived it from some other point of view. But here it came from the assumptions that I made precise. Now, an important point is that it came from perturbation theory here. Okay? And so you can ask, what about non-perturbative? What about finite lambda? What do you do with this at finite lambda? And the answer is, the only answer I'm comfortable with is that we do the perturbative analysis, and then we assume that we can take this differential equation as defining the theory at finite lambda. So we're going to define the finite lambda story by demanding that this differential equation be satisfied. And of course, the differential equation requires initial conditions. So we will require that the initial conditions are that the partition sum at lambda equal to 0 is that of the original CFT. Okay, so from my perspective, the way the model is defined is perturbatively, with this being an extra assumption. Any questions?
I have a nice question. So you have the recursion relation and you have the perturbative expansion of Z. And from there you can uniquely fix a differential equation?
Yeah.
Okay.
Say again? I mean, it's like 5 lines of algebra, if you are slow like me.
And secondly, when you claim that it could be that you define it to be non-perturbative, you assume that there couldn't be explicitly lambda dependent, which goes to 0 when you set lambda to 0.
Say it again, non-perturbative terms.
I mean, if I add a
Look, again, everything, I'm not holding back anything. I mean, I told you exactly what I'm doing and what I'm assuming. So I got, I concluded that the ZPs satisfy this. This is the same as that for the perturbative series. And now I assume that the definition of my theory is such that this equation is valid for finite lambda with the initial conditions I wrote here. Now we'll discuss a little bit about non-perturbatively, but this is what I'm saying right now. Yeah. Yeah, it never ends. I think it ends here. I hope I put all the brackets correctly here. Yeah, it looks okay. Sorry. Well, look, this the correct version of this equation appears in the paper. So, if you ever want to use it for anything, just look at the paper. Okay, so that's one comment, that the non-perturbative definition, from my perspective, is this. I want to make a couple more comments about this. I want to make a couple more comments here. So, what else do I want to say? If you take this differential equation and write it in its original form, which I've done already twice. Let me do it one more time. And so if the partition sum satisfies this equation, you can just evaluate the left-hand side and the right-hand side and demand that the coefficients of each exponential is the same. So, you apply this operator to the z, you get something. You apply this operator, you get something else. And so you get some equation that leads to precisely this Berger's equation that we've seen. Or to be more precise, it is the special case of the Berger's equation that applies for the conformal, where the original theory is conformal, which is some special case of that. So the solution of this equation, how do I write like this? So the solution of this equation looks like this. So En and Pn are the energies in the original theory, the conformal field theory, and we see the explicit lambda dependence here. And so I want to talk about some properties of this, separating the two cases that already were separate in Sasha's lectures. So which in my notation are lambda larger than 0, which I think is what he would call alpha less than 0. So I'll discuss that first and then talk about the other thing. So if you ask about what this thing looks like at high energies, so of course before we turned on this lambda, we had just a standard CFT kind of spectrum. But now we have a Hagedorn spectrum. You can easily calculate what this is. And so you get something like this, that the number of states goes like the exponential of the energy. And remembering that this lambda is T over R squared, the Hagedorn temperature, so the R's cancel, and the Hagedorn temperature just depends on the coupling, not on the radius. So you get a Hagedorn spectrum at high energies with some beta Hagedorn that goes like square root of T. Yeah. Yeah. So this formula, so I told you that this is going to be some function, some unique function of En, Pn, and lambda. So there's one function into which you plug in the undeformed energy, and that's exactly what's written here, right? Well, it's an example. This function is an example of this. In other words, it's not like for every state you have to invent some new function, okay? Yeah, so like I said, there's this Hagedorn spectrum. And another issue is the ground state energy, which I think already also appeared here. So for the ground state energy in the undeformed theory, you have some formula like this. RE ground state is equal to minus C over 12. And of course, P equals 0. And so if you plug this into here, you get that if pi lambda C over 6 is not smaller or equal than 1, you're going to run into trouble, like there's some square root here it goes complex. If you use this equation, there's some constraint like r is larger than square root of pi ct over 6. So what is the physics of this? So, yeah.
The first thing, a prefactor would also not contain R in the rowy density of space?
I didn't look at it, I'm not sure. Yeah, I don't remember. This is a pretty easy question, but one that I didn't look at for a while. So what is this thing here? Well, so this is basically the statement that because of this behavior, we're dealing with a non-local theory. And if we try to put it on a circle that is too small, it objects in this way. So we have to demand this for, if you want the theory to be unitary, the eigenvalues of the Hamiltonian to be real, you have to demand this. And it's not that shocking. I mean, it's a non-local theory. So that's one thing. But then there is also another thing that we need to worry about, and that is that the partition sum does not converge because of the Hagedorn behavior of the spectrum. So, the trace here states with some energy come with this multiplicity, and so if tau 2 is too small, we're going to run into trouble. So the Hagedorn high energy spectrum implies that tau 2 must be larger than square root of pi c over 6 lambda, turns out, lambda over 6. Now, what is this tau 2? So suppose you have a square torus, right? So you have, say, 2 pi r and beta here. So tau 2 is just the ratio of beta to 2 pi r. And this ratio has to be larger than this, which means that beta must be over 2 pi, must be larger than that same number, pi ct over 6. And again, it makes a lot of sense. So just like you don't want the spatial circle to be too small because of the non-locality, you don't want the time circle to be too small because of the non-locality. And so this is basically the non-locality scale of the theory. So that's a feature of this whole story. And that doesn't seem to be too painful. Moreover, these two conditions are interchanged. So these two conditions, the one on the radius and the one on beta, are interchanged under modular transformations in the sense that, a part of the modular transformations that I mentioned give this. Where tau 2 tilde is 1 over tau 2, and lambda tilde is lambda over tau 2 squared. So, so you can easily convince yourselves, I don't have time to do it necessarily, that the two constraints that I mentioned are interchanged under these modular transformations, and that's this familiar story that we know and love, that the high energy density of states and the ground state energy are related by this kind of thing. Any questions? Oh, and one last thing that I forgot to mention before is, so remember I told you that non-perturbatively, or if you wish at finite lambda, I took the attitude that I want to define the theory by imposing the differential equation with the initial conditions at lambda equals 0. And then Schumann should ask me all sorts of questions about is it well defined, non-perturbative, whatever. And so the answer mathematically is that that differential equation with initial conditions at lambda equals 0 for this sign of lambda determines this function z uniquely. So z of lambda and tau for lambda larger than 0 is uniquely determined by the differential equation I wrote down and the initial conditions at lambda equals 0. So that's basically everything I have time to say about this lambda larger than 0 theory. Now what about the lambda less than 0? So yeah, I don't know. Do you want me to say something about the JT bar or? Okay. So I'll be a little bit more brief. So for lambda less than 0, everything is worse. So we heard some things about, this is like the alpha larger than 0 in Sasha's language. So what is worse? Well, so one thing that is worse is that highly excited states have complex energies. So in my notation, if 1 plus 2 pi lambda REN is negative, so if lambda is negative, that just means that EN is large enough, the energy is in the undeformed theory, then you have complex energies. And so this leads to questions about unitarity. Yeah, so somebody, I guess Sasha mentioned, what if we try to cut it off over here? But then there's no way that modular invariance will work. So this is all sort of an open question. So that's one thing. Another thing is that the differential equation plus the initial conditions that I imposed do not, in this case, determine this z of lambda and tau uniquely. So in particular, there are e to the minus 1 over lambda corrections to z. So the solution has these kinds of ambiguities that we studied quite a bit, but I don't have time to talk about them. You can read about them in the paper. Okay, so the bottom line of this part of the talk, which I guess is most of the talk, is that in this TT bar case, there are these two separate cases, one of positive lambda or negative alpha, which seems very reasonable. There's non-locality, which, say, for the partition sum, leads to these kind of constraints. But this is not necessarily a killer, and the other sign looks much worse. So any questions about this? All right, so in the last 10 minutes, I'll talk about what I was going to talk about for maybe half an hour, which is the JT bar story. So I will have to be very brief, but again, since there is a paper on this, if you really are interested in the details, you can find them there. So basically, here the starting point is a CFT with a holomorphic conserved current. So there's some J that satisfies the equation d bar J equal to 0. And what we want to do is deform it in such a way that the leading term is proportional to JT bar in the notation we've been using. And then there are, again, higher order corrections. And the higher order corrections are tuned in such a way that so this is something that Shumangshu, Amit, and I did last summer, is we pointed out that there is a way to make the full theory have a holomorphic conserved J. In other words, there is a current J, which of course is not the same as the current in the original theory, that remains holomorphic and conserved. I guess this was following some ideas by Monica Goikam. That is correct. Now, so there are some arguments that we gave in that paper with Shumangshu and Amit about why this is a reasonable thing to happen, but I'm not going to review them, especially not in 8 minutes. But what I want to do is very briefly explain how the logic of this lecture generalizes in a nice way to that case. And so the idea basically is the following. So in the original CFT, because of the fact that we have this what
I'm trying to read this.
mu JT bar?
No. This full theory has a bad what?
Oh, full theory has a holomorphic conserved current.
Oh, okay.
So this is the assumption that is being made, and I can explain to you why it's a reasonable assumption. But basically, the idea is that before we did anything, it's natural to turn on a chemical potential for this charge that couples to this J. So that's a standard story, right? So in addition to the terms that I keep writing, we can also turn on this chemical potential. And there's a standard story that under modular transformations, if you make this new transform like this, where this transformation basically has to do with the fact that the current it couples to is holomorphic, you get some generalization of the equations that we wrote. In other words, this is some Jacobi form, where K here is the two-point function of J. So the basic idea is that you can repeat everything I said. You can define some partition sum, which depends on tau, nu, and some mu hat, which is this mu divided by r, just to make it dimensionless again. And the same kind of argument tell you that it's a Jacobi form with both nu and mu hat transforming. So nu transforms like this, and mu hat transforms to mu hat over C tau bar plus D, which has to do with the fact that it's not marginal on the bar side. And then you can just run the whole exercise again. So, so here we connect to some question that Dan asked like an hour ago. What about this uniqueness story when I have two examples that are different? And the answer is that in the first story, the energies were only functions of the, it was assumed that the energies were only functions of the energies and momenta of the undeformed theory. And here, in addition to the fact that it's not Lorentz invariant, like we heard before, it's also the case that the assumption is that the energies of the deformed theory depend on the energies, the momenta, and the charges of things in the undeformed theory. So, the assumption is different, so the conclusion is different. So, in other words, the assumption there is not satisfied here, to say it in a different way. Not just because of the Lorentz, but also because of this. Anyway, so you turn the crank, and you get some differential equation that this partition sum satisfied. That I'm going to write it not because I need to, but because Meet and I somehow managed to get it. So you get some equation that looks like this: I pi k mu hat nu over 2 tau 2 derivative of z equals tau 2 d nu d tau bar of z minus I pi. Okay, let me write it on the next line. Over 2, 1 over 1 plus I pi k mu hat nu over 2 tau 2 d tau bar of z. So, more seriously, the reason I wrote this is that it's kind of remarkable that making qualitative assumptions about things, like I did throughout this lecture, gives rise in the end to this kind of thing. Very specific, very detailed differential equation from which you can read off the spectrum, again, like we did in the other case. And so let me finish just with the formula for the spectrum, and then I'll stop, because I think Amit will use this formula for the spectrum next week. Where is it? Yeah, I don't know. Well, whatever. I mean, there's some very detailed, complicated formula for the spectrum that comes from this equation. Of course, there's some analog of Berger's equation that you can derive from here. And okay, yeah, but you don't have to set it to 0. So, so the basic message is, I would say, that this theory exists. It has been analyzed from 2 different points of view, from the point of view that I did not discuss here at all from our paper with Shumangshu and Amit, and from this modular properties point of view. You get the same answer for the spectrum, the charges, and all of that. And it has to do with a lot of interesting string theory models that Amit will talk about next week. So let me stop here.
I'm sorry. I have a remark, of course. I mean that what you said about it concerns the power series expansion of the partition sum, modular invariance and stuff. Your statement about uniqueness is very interesting. Uniqueness of partition of coefficients, right? It's very interesting, but it definitely contradicts to my understanding of what the renormalization theory tells us. And if the chairman would allow, I will ask for 3 minutes.
So here,
very precisely, what renormalization theory would make us to expect about the solution to this problem.
I'm dying to hear.
I'm sorry. Yeah, and so I just stated, and then we can settle it one by one. Well, hopefully with a bottle of something good. All right, so let me. It's going to take 3 minutes. All right, and I will try to use the same notations. Actually, I insist on using the same notations as David did. So we have a partition sum and its expansion, right? The z, which is lambda to the p, right? That's what your notation. Z sub P,
Sum
right?
over P.
And sum over P, yes. Sum over P. So we are demanding some sort of modular invariance or whatever physical properties the quantum field theory is supposed to bring up to this ZP. And we do it order by order in lambda. And then we ask what is ambiguity in the solution of this properties is. So we want to say, to ask, suppose I have two different solutions. I'm trying to restore your formulas. And so we are looking for some sort of kernel, all right, to the right-hand side. What kind of ambiguity would be there? And term by term, P equals 0, that's starting point. In this particular case where we have lambda, dimension 2, conformal field theory, everything. Now, P equals 1, all right, so this is, let me call it KP, right? So in that case, the solution is unique. K1 is empty. That's the.
So can you say again that ZP and Z prime are demanded to satisfy what property?
Modular invariance in your case, or I can supplement it by whatever properties quantum field theory is supposed to.
Are you supplementing or not?
I'm not. I mean,
But he has
I
these
mean,
crazy requirements on the energy, right?
what crazy? What was crazy about that? They were very.
Talking to the author of the crazy requirement.
They were, I think, sensible in many respects. So I don't know how to. So let me call it K1 is equal to 0. Okay. Now P equals 2. I look at your equations. I didn't. I mean, I am too slow to follow. K2 equals 0. P equals 3. Now you have one-dimensional K.
Sorry, one-dimensional K?
Yeah. So there is ambiguity in the solution, Z3 minus Z3 prime, which I call K3. Okay, and I produce for you the basic vector in this, and it is K3 is integral over torus expectation value of t squared, t bar squared of x d2x over torus, and this is CFT expectation. All right, so this is K3. You are invited to check that adding K3 of this form to your solution would satisfy all your requirements if you didn't make mistakes. Now you can follow it, right?
Wait,
KP.
No, but I don't think so. There is a contradiction.
Yes, there is a contradiction. That's what we are going to settle one-on-one over. Yeah, of course. I mean, the most likely resolution is just me being stupid, misunderstanding renormalization theory, and so forth.
So can you say a few words about why you think that?
Let me finish the sentence, and then I say.
Sure.
Fine. Let me just, because it's going to be clear when I say what KP is. KP is some when P grows, the dimensionality of this kernel grows, and eventually the dimension of P of KP is going to be a dimension. If you remember, if anyone remembers the dimension of this F vacuum, the dimension of F vacuum P hat, and this is level P subspace in the level decomposition of the vacuum modular of the vacuum representation of the Virasoro algebra. So this space is at each level is spanned, is furnished by possible counterterms. All right?
You mean connection?
Counterterms. I don't know what connection means in this case. What kind of bundle we're considering?
So, Sasha, I'm confused. So are you saying you can just add this term to the action without adding TT bar, and that also would produce for you a well-defined set of RG flows?
Well, the randomization theory tells us that if you do perturbation theory, you can define yourself the regularization scheme and subtraction scheme. All right? And the subtraction scheme leaves behind ambiguity in adding this term. After you do this regularization and subtraction, you are free to bring cutoff to 0 at this order. And then all kind of properties which David insists are supposed to get restored, including modular invariance. So I mean, generally, if you have some finite cutoff, you really don't expect the modular invariance, because if you tilt your torus like this, you will have small distances, and your cutoff wouldn't fit. But if you remove the cutoff before, I mean, your modular invariance is going to get. I'm sorry, I'm taking too much time.
I thought that this is essentially what you're saying is what Ofer said, that you are thinking about this bigger space that you talked about in your paper in the beginning, in the sections before 5.
Right.
And
but I'm talking about this problem, which you.
No, but I think in our language you are talking about systems which have more than one scale.
No.
No, you can pretend like you can make them.
Pick them all to be the same.
Yeah. Now, if you pick them all to be the same, then the question is, do the energies satisfy this constraint?
Which constraint?
That my constraint number 3, that the perturbed energies are only function of the.
I probably misunderstand this question. If you say that perturbed energies are uniquely determined by unperturbed energies, then your statement becomes tautology.
No. So the question is, so there's some universal function of the unperturbed energy that gives the perturbed energies.
It's
but
independent of N, right?
yeah, but we are not. But the question is, what is the function?
But it's sort of unique function which uniquely determines perturbed energies in terms of. Then your statement about uniqueness of partition functions becomes empty statement.
Well, so okay. Well, I've made a lot of empty statements in my time, but the statement here is that the requirements, this modular invariance, and this determine the function. Perhaps where I'm missing what and this.
What
else? So you're essentially asking what else could have happened, right?
Yeah.
Okay, so the answer.
No, I'm not even asking. I'm telling you that if you just take a.
No, but this must contradict something we're doing.
Yeah.
So the question is what?
Yes,
right?
yes, exactly. That's my point.
Assumption 3
I think
is
it's
so
assumption
strong.
3.
It's
Assumption
so strong.
maybe I called it crazy. Maybe I should call it crazy, but it's very
It's a
strong.
very
Yeah,
strong
well,
assumption.
I don't even understand what it means.
No, just compute at leading order. Can you compute how the energy levels change when you add this, and do they only depend
Yes.
on the energies in the momentum?
Well, if I allow this term to squeeze in,
Yeah.
it would change the energy levels.
But would it change it in a way that only depends on the energies and momenta of the original states? Or
Oh
would
yeah,
it also
oh yeah.
It wouldn't mix
not
with the other.
I tell you how it changes. I can write you a formula. Delta, the delta En, which is generated by this R, is the expectation value of t squared, t bar squared. You could tell it for me yourself. All right.
This doesn't have off-diagonal terms.
This might have a diagonal terms, just like any other operator could have, but we are interested in the diagonal terms.
So it's only the diagonal which would come here.
Well, it's first order perturbation theory.
Well, sorry,
Yeah,
isn't there
but
an
second
issue?
over there, they come in.
Sorry, but isn't there so naively, right, when you do the deformation of the action, you can add TT bar, but you can add TT bar squared and TT bar.
Exactly, that's what I'm saying.
Yeah, but then there's this power of little t that goes in front. And then, so he wrote this order t squared in action, right?
Yeah, no.
Lambda. Okay, okay. So what I'm trying to do is, okay, so there is a, I'm sorry, there is t times this tt bar, and I'm trying to add the counter term, which comes with t squared, and it comes with, actually, it comes with t cubed, because that's why this one is forgiven. Then it comes with t squared, t bar squared. And actually, if you in any reasonable scheme, if you take a tt bar flow, this guy is going to appear with precisely measured coefficient, which now though depends on the precise regularization and subtraction. No, but okay. Once you have a regularization scheme, then it would come out unique for TT bar flow.
Look, it sounds like there's a sharp contradiction.
Yes.
No.
Yes. Yes.
I don't, no, because naively you should just expect it depends on the cutoff if you put in arbitrary. I thought the fantasy was that if you choose these zones just the right way.
No. You throw yourself. You take yourself in some regularization scheme. I don't know, lattice, whatever. Then second order of perturbation theory, third order of perturbation theory here would involve a divergence, right? You add this with divergent coefficient to compensate divergence, but then you are left behind. You are left with the finite part behind. That's a standard ambiguity in the under normalizable perturbation theory. That's what I'm saying. And this ambiguity is just ambiguity of theory. It's ambiguity in producing solutions which satisfy all physical properties like modular invariance and so
usually the theory you make like that doesn't make sense at higher.
People need to have coffee.
right, but that's the property of the whole.
Your lecture.
That's the property.
So we will be back past 11.
I'm sorry, I didn't make people ask interesting questions.
No, this is a very interesting question.
No, I understand what you're saying.
How do you define this operator? I still don't understand how this operator is defined.
Oh yeah, it's
Another TT-bar, I would say, does have shortest singularities, which are totally
Yeah,
reversed, right?
but naively, once you remove them to define an operator, then is this supposed to be a primary operator? I mean,
Yeah.